5 is universal gravitation. So we're going to get at a law of gravitation. And if you remember back to our light experiment at the beginning of the year, where we did the light sensors made out of wax and determined the relationship around a light source, we had a light source, and we realized that surrounding the light source, the light intensity would be based on how the light spreads out around a sphere around it. So that as you get farther away, um, the light intensity has to spread out on a larger sphere, and the one that's left, and so that it will be weaker per unit area that it is. So it spreads out around that sphere. Well, the same thing happens when you go in gravitation, when you go around, say, the planet Earth. All its blue and land and stuff like that. That the gravitational field, or the pull around that, around the planet Earth, will be one thing in one position out, say, in close space, based on the mass from that. And then as you get farther out, that field will weaken because it's spread out on a larger surface area. So we'll apply the field that we learned about light intensity to the gravitational one. So we've talked a lot about gravity, and we've used it. We've used it as an acceleration, and we talked about the force of gravity with weight. Newton is credited as being the first person to understand that gravity was in fact a mass attraction, or attraction between two masses, which is in plural situation based on Newton's third law. The force on one mass exerts a force on the other mass, and vice versa, equal and opposite forces. The Earth is a sphere. The effects of gravity should vary with the square of the distance, just like with our light experiment before. So we came up with this relationship, that F was related to the two masses involved in the interaction and the distance, the square of the distance they are from each other. And now the units wouldn't work out on this. It would be kilograms times kilograms over meters squared on the right-hand side and newtons on the other. So we need to have a constant to make this work, and this gives us the universal law of gravitation, which has big G, constant big G, times m1 times m2 over r squared, and it looks like that. So that's an important formula because it allows you to calculate what the gravitational force is between two massive objects separated by a distance from the centers of mass, r. Now this G is called the gravitational constant, okay? So big G is the gravitational constant. Now we don't know what that is yet. So we could see that we could get this force of gravity. We could even call it Fg. And if we could figure out what big G was, okay? And we could make the units balance, so we could figure out the units of G. Let's see what the units of G are. Since we have newtons over here on this side, which is kilograms times meters per second squared, and over here we have kilograms squared over meters squared, Well, what will G be? Well, G has to cancel one of the kilograms. So we could see that it has to have a kilogram on the bottom, and it needs to leave the meters cubed so that we left with the meters on top. And we also need there to be seconds squared in it. Now, so the units for G are meters cubed over kilograms times seconds squared, because meters cubed over meters squared would leave you with the meters, and kilogram squared over kilogram will leave you with kilogram, and seconds squared have to be added on there. So now we know what the units are of G, but we don't know what its value is. We have to go back to see how that's figured out. Okay. Well, oops. Tycho Brahe was collecting data about planet positions at different times of the year. And this was a few decades before Newton started working on his gravity ideas. And he spent over 30 years collecting data on the planets, watching them go through the sky, his spending nights observing the location of these planets. And then his data was studied by Johannes Kepler. And he was the first generation of university-educated mathematicians after the Black Plague. And he went through Brahe's data, and he came up with 3 rules about planetary motion. The first rule was that all the planets travel in ellipses. The sun at the center of one foci. Now, a circle has a center, and an ellipse has 2 foci. So here's an ellipse in blue, and we see that here's 2 foci in green. There's one there and one here. And that the sun is the center of one of those foci in the ellipse. So planets travel in ellipses around the sun, and the sun is one foci. The second of Kepler's laws was that planets do not travel at constant speeds. But in a given amount of time, they always sweep out the same area. So if we go down to our figure down here again, we see that even though in position A1, the Earth moving around the sun has moved less amount of distance than in position in the A2, that the area of A1 and A2 are equal areas that are swept out. The third part, which is going to be most critical for us, is that for each planet, out there in our solar system, the radius of the average radius of of the of the path around the sun, and cubed over the period, the time it takes to go around the sun. Oops, that's not cubed, sorry. That's squared. Squared was equal to a constant. And when Newton started to look at this last idea, he realized the reason that this was a constant was based on circular motion. And he realized that for circular motion, especially for the circular motion at a constant speed, so there were variables in it, but when you looked at the average radius and all that, this worked out, that he realized that it was based on the fact that the centripetal force that was keeping it, which is always a combination of other forces, was due to a gravitational force between the planet and the sun. So what was causing it to go around at a certain period, at a certain radius, was the centripetal force, and that centripetal force was the force of gravity, Fg. So that was important to realize, because it will come to our equations of planetary motion. Now, it still doesn't give us what big G was. So unless someone could figure out what the mass of the sun was, because if we had the mass of the sun and the mass of Earth, then we could get, well, we knew what the mass of Earth was by estimates of density and stuff. But we didn't know the mass of the sun. Unless we knew that, we wouldn't be able to get G. But in 1798, 110 years later, someone came up with a way to get the actual value for G. Henry Cavendish is credited with an experiment carried out in a barn in England where G was first found. But John Mitchell came up with the idea for the experiment, but he died before it was finished. And this experimental setup needed to be in a barn because it involved large masses, large areas. And so from the ceiling of the barn was hooked up a value in our system, a large pole centered in the middle, and it was able to turn. And as it turned, you could measure the amount of torsion on a spring. And then hung from that were some mass balls from either side. They were allowed to go into balance. And then you could look at what the value was on this torsion measurement there. And if it's just sitting, it would just sit at a certain value, as precise as possible. And then a very large mass, large as possible, was hung close to and separated by a certain distance apart from one of the masses. And that caused the gravitational pull to pull this one that way. And then the extra amount could be read on the torsion spring balance. How much more twisting was occurring because of the gravitational pull between the large blue mass and the small red mass. It would pull it towards it, and so you could look at the scale and say, okay, it's pulled it this much more. That much that it pulled this much more was Fg. force of gravity between the two masses. And because, if we look back at our formula for Fg, big G m1 times n2 over r squared, if we know what r is, we know what the two masses are, and now we can get Fg, we can calculate G, and when Cavendish did this, came up with a value of G that's really small, 6.67 times 10 to the minus 11, putting it together with newtons in units, we get newtons meters squared over kilograms squared are our units for G. Now G was known. So with G being known, we could come up with an actual mass of the Earth. Okay? So we could estimate what the mass of the Earth was previously, but with this we could get the actual measurement. So big G is known, and let's calculate the mass of the Earth. So in our formula, Fg is big G m1 times m2 over r squared. Well, in this case, let's take any mass object. The radius of the Earth is known. Which was 6.4 times 10 to the 6 meters. So we know that. Let's take any object on the surface of Earth. We know from the previous that that is m times the acceleration g. Then we have big G in here times m times the mass of the Earth over 6.4 times 10 to the 6 meters squared. Well, so the mass is on both sides of the equation, the mass of any object on the surface of Earth. So that will cancel out. So the mass of the Earth, if we solve this, equals G times 6.4 times 10 to the 6 meters squared over big G, which would be equal to 9.8 is G meters per second squared over 6.4 times 10 to the 6 meters squared over 6.67 times 10 to the minus 11 newtons times meters squared over kilograms squared. And if you do that calculation out, you'll get 6 times 10 to the 24th kilograms for the mass of the Earth. So the important thing is from this experimental setup, measuring the extra torsion on a spring, you're able to get and calculate the value of the universal gravitational constant, big G, 6.67 times 10 to the minus 11 newtons times meters squared per kilogram squared. Okay. Okay. Let's take Kelly's little sister. Okay. Now Kelly's little sister has a mass of 30 kilograms, and her friend has a mass of 85 kilograms. They're standing 3 meters apart. What is their gravitational force? Well, this is a simple plug-it-in problem. Fg is big G times m1 times m2 over the distance they are apart squared. Big G is 6.67 times 10 to the minus 11 newtons times meters squared over kilograms squared times the mass of Kelly's sister, which was 30 kilograms, times the mass of her friend, which is 85 kilograms, over the distance they are squared. 3 meters squared. And if you calculate that out, you'll come up with a small force between the two of only 1.89 times 10 to the minus 8 newtons. Try that on your calculator. So you'll have to get used to using the calculator with scientific notation, and we'll have some practice with that in class. Okay. The mass of the sun is 2 times 10 to the 30 kilograms, and it's 1.5 times 10 to 11 meters away from us. With what force does the sun pull on a 60 kilogram person on Earth? Fg is g times m1 times m2 over r squared. Well, what force is, that means Fg that we're looking for. I mean that we're looking for. And big G is 6.67 times 10 to the minus 11 newtons times meters squared over kilograms squared times the mass of the sun times the mass of the person times the distance they are apart, and if you calculate that out, the sun is pulling on the person and the person is pulling on the sun in the other direction, 3.557 newtons, 0.3557 newtons. So, not very much. The Earth is pulling down on that person at approximately 600 newtons. However, still a significant amount. Okay. So, let's look at the concept of the universal gravitation in terms of little g. So, Fg is g times m1 times m2 over r squared. But when you look at a certain object, then you get g times that m, and the other one's the mass of the Earth over r squared. So these m's cancel, and a formula to calculate the gravitational constant, or the acceleration due to gravity, little g, is equal to big G times the mass of the Earth over r squared. Now, you could use this for other planets, so it doesn't have to be the Earth, but we could write this in general for g, little g, for any planet based on the radius of the planet. Okay, so for example, what is the value of g on Jupiter? Should have capitalized that. The radius of Jupiter is 7 times 10 to the 7 meters approximately. And its mass of Jupiter is 2 times 10 to the 27th kilograms approximately. So we could just calculate it. G for Jupiter would be 6.67 times 10 to the minus 11 newtons times meters squared over kilograms squared times the mass of the planet, 2 times 10 to the 27 kilograms over the radius squared. And if you do that out, you'll see for G is 27.2 meters per second squared. So we know the mass of the planet, the radius of the planet, we can get its value of the acceleration due to gravity, g. Now, we could also see that the farther you are away from the planet, g is going to decrease in an inverse squared relationship. So if you were on the surface of Earth, okay, at just the radius of Earth away, and let's say you had a value, it was a 10 kilogram object, so it would be like 100 newtons out there. But if you were to move out into a distance of 2r, 2 times the, out into space, 2 times the radius of Earth, now your g, you would be doubling the distance you are away, and g would be reduced by 2 squared, or 4 times. So you would be only at 25 newtons right there. If you were to go out to 3 radiuses of the Earth, then it would be 9 times less, or a little less than 10. 4 times the r would be 16 times less, whatever that is. It's sometime out there. So you would have this relationship that it would never decrease to actually get to 0, but it gets small. The value of the acceleration due to gravity gets smaller and smaller as you get farther away from the massive planet or whatever massive object you're looking at. So let's see, what is the acceleration due to gravity at the space station? Okay. Well, sometimes you might think, well, they're floating out there. They show pictures of them floating, so we're in gravity-free space. But that is not true. We've talked about how, in fact, they're falling towards Earth up there. And as they fall towards Earth, it appears that, or it seems like they're floating, but we're just falling in an orbit around Earth. Okay. And we talked about an elevator falling in free fall, and the stuff in the elevator, as it fell, if you had things in the elevator, they would start to float around you. And that's the same thing that is happening on the space station. If it goes around in an orbit around Earth. So what is the acceleration due to gravity up there? It's not as strong as it would be on the surface. Well, the altitude of the space station is 3 times 10 to the 5 meters up. And the radius of the Earth is 6.4 times 10 to the 6 meters. So g would be big G times the mass of Earth times r squared, or 6.67 times 10 to the minus 11 newtons times meters squared over kilograms squared times the mass of the Earth, which is 6 times 10 to the 24 kilograms, times the radius squared. But the radius from the center of the Earth would be 6.4 times 10 to the 6 meters, the radius of Earth, plus our 3 times 10 to the 5 meters squared. And if you calculate that out, you'll see that g is 8.9 meters per second squared out at that altitude of the space station. Okay. Well, as in orbits As objects travel in circles using gravity as a centripetal force, okay, we saw that the Fc centripetal force is Fg. Now, from this, um, all objects in the same orbital path must have the same speed and period. So any object that satellite or space station or whatever it is that's going around Earth at a certain altitude in the same orbital path, it will have the same speed as others going around and period in that path. So if we start with taking the formula G equals G times the mass of the planet over r squared, and if we realize that G is an acceleration in centripetal movement, then from before, remember AC was V squared over R, so V squared over R is G times MP over R squared. And if you solve that for V, you would get the square root of G times MP over R will give you the velocity that an object is moving around a massive planet is the value of G times the mass of the planet over the R, which would be the radius of the planet plus the altitude that you're at. Okay? Now, on Earth, of interest a lot is the geosynchronous orbit, or one that actually where the period of the satellite is the same as the planet that it orbits. Now that's important because if as we know, the Earth turns on its axis. If we want a satellite to be directly over the same location at all times, okay, for spying purposes or cell phone purposes, things like that, telecommunications, then what's the orbit that we need to, the altitude that we need to put it at so that it gives a specific, it stays in that, as the Earth rotates, it stays directly over it. That's called a geosynchronous orbit. So in that case, well, you remember the period is 2 pi r, the circumference of the circle, over v. And if we remember, well, just from our v right here, we could plug that in, square root of g mp over r. Okay? Now, if we square both sides, we get t squared is 4 pi squared r squared. The square root of the square root goes away when it's squared. The square of the square root. And then flipping over, we get t squared, or bringing the r up, 4 pi squared r cubed over g times mp. And then t, then if we take the square root again, is the square root of 4 pi squared r cubed over g times mp. And that gives us the period for a satellite orbiting a planet. So what is the geosynchronous orbit of Earth? Well, 24 hours, you can calculate out, since you would want the satellite to go around every 24 hours, because the Earth rotates every 24 hours, is 86,400 seconds. So if we take our period, 86,400 seconds, we set that equal to the square root of 4 times pi squared times r cubed over 6.67 times 10 to the minus 11. I'm going to leave off the units for ease here, times the mass of the Earth, which is 6 times 10 to the 24 kilograms. So let's square both sides. Well, I'll leave this to solve for in class for sake of time. And there's obviously a lot that we need to go over with that in practice. So that will end, and that makes it a long 36-minute video, but